Welcome to Bridge the Gap, the physics-oriented podcast of the TU Graz,
where we give insight into physical topics and the life of scientists.
Hey Daniel, what do you know about paper?
Not much. One can write on it?
Yeah, me neither. I dare say I have a paper thing knowledge.
That's what I thought.
But I have another one for you. Why can you not make a joke about paper?
I don't know, but I'm sure that you can.
Yes, I can, but it would be terrible.
Like your attempt at making jokes? Jokes aside, we were wondering what some of our students and friends know about today's topics, and here are some of their answers.
Very curious to hear them.
So paper is made of cellulose, and looking at it from the production side of things, it is made from wood originally. What does it have to do with physics? Well, everything has to do with physics. You could look at the surface, but you could also, use the paper to make a paper airplane and calculate its trajectory.
In the first place, paper is matter, and it's made of some structures, some complicated structures.
Paper is a sheet of paper, or perhaps I'm biased. For me, a paper is a scientific article. It's made of chapters, and it has to do with physics because every scientist, at least once in its life, publishes his or her research on a paper.
Today we will discuss paper and other porous materials and the most recent discoveries in this area with Karin Zojer.
She's a professor at Graz University of Technology, and I'm sure we will have fun with her. Today with us we have Karin Zojer. She's a professor of solid-state physics at the University of Technology in Graz, and with her we'll talk about transport through complex materials. Let's just say this. So Karin, can you introduce yourself? What's your field of research, your background?
Yeah, thanks for having me, in fact. And just to give you a brief idea where I come from. So I'm a person who would like to model and simulate processes. And in the course of that, I got interested in describing, understanding, and predicting transport processes. And as you already heard, I'm associated to solid-state physics. So the solid state comes into the game that some of the solids that we are dealing with lack order and happen to be of very complex composition. And we would like to learn how, for instance, charges, but also gases, particles, for instance, can be transported through such solids.
One of your current main research topics is paper, which is, to my understanding, a so-called multi-scale material. Can you tell us a bit what that is?
So I share the same view. So we have multiple scales to consider when we talk about paper. That comes already from the very composition of paper. The paper that we have in front of us is usually made of fibers. In our case, mostly fibers that have been retrieved from wood, and these fibers are combined in networks, and these networks are stacked on top of each other in a paper machine, giving rise to something that is essentially a network of fibers with a lot of porous space in between. So, and what we get out is some material that is enormously long. So that's a big roll on the paper machine, which is 4 meters wide and happen to be in the order of 40 to 100 micrometer thin. So you have immediately a number of dimensions to consider, this being the long sheet scale, the thickness scale, and then of course in between the fiber scale, which let's say it's in the order of 15 micrometer.
How is it even possible to simulate something like this, where you have to consider so many different scales?
That's now a matter of community, I have to say. So we have a very, very flourishing and active research where more and more researchers come together and add experience from different scales. So I'm, for instance, the one who is looking in the so-called pore scale, so what is going to happen in the pores in between the fibers. So I'm the person somewhere in between of everything. Then we have particular mechanical engineers that are very smart in trying to mimic the behavior of the fibers and what is happening if you stack the fibers to form a fiber network. And this is giving us information how the pores are formed, what the geometries look like, what kind of properties we can expect on that side. And on the other hand, these fiber networks are taken over by other engineers who can then really go to the sheet scale and have a look what the mechanical properties are, depending on how homogeneous these fibers are laid out or whether we have defects, what is going to happen. And there is, and I possibly will comment on that a little bit more deeply later, there is now also some additional experimental insight possible that helps these efforts a lot.
So you said you're a computational point of view. You come from a computational point of view. So how do you model transport in these materials? Because before you also said normally it's just the focus is also on solids. Now we are talking about porous materials. So which are the methods or the tools that you can apply to both of these areas of expertise?
So this, to be honest, depends really a lot on which kind of transport you are interested in more detail. So for us, it turned out that the most important thing to make progress in was to look in how volatile organic compounds, for instance, aroma compounds that are in your food, can be transferred through paper. And then we have, if you like, more diffusive kind of motion. Mm-hmm. And we had to decide and we had to figure out what is the best mathematical model to tackle that. So also the method was not clear up front. So is it really necessary to microscopically see what the molecule is doing in the paper? Or can we do something that is a bit more on a grander scale and we have an effective behavior covered? It turns out that experiments were giving us the clue. I working together with experimentalists, and with the help of very well-designed experiments, we would clarify the time scales that are relevant and the length scales that we have to incorporate in going to make predictions. And this was then pinning down the method we would use. In our case, it's just really now a reaction diffusion equation. Mm-hmm. That is a set of partial differential equations that have to be solved.
Naively speaking, one would think that something so common as paper is already well known. So what are the new things you discover?
That is a great question. Exactly, that was my first question that I had.
Our first question, actually.
So paper's around for 3,000 years. So what? But then I was also posed to questions, and I was thinking, well, these are questions that should be given to another researcher who's more proficient with the topic. You will get an answer, and then you say, well, doesn't this imply such and such? And you can play this game possibly 2 further stages, and then there's no answer any longer, because we do not understand certain very fundamental microscopic things that happen. So in that sense, there's a common wisdom about paper, but it's not enough to redesign new functionalities in the paper. And this is something what is driving the whole story in the sense. We would love to understand enough to think about whether this regrowing material of this fiber-based paper can be also used in other applications, can be combined with other materials just to save plastic. Go with less plastic and have a paper functionality on top. This would be, for instance, one of the nice things. So what we have learned in detail is first of all, and don't laugh at me, is just really getting a toolset of methods together with which you can tackle these things in the first place. So we had a number of failures and we have successes, and it's very important to communicate what kind of point or what kind of approach does work and which kind of approach does not work, why. That's one of the things. I understand it's very technical and not overly spectacular, but it really brings the field forward. The second thing is what we constantly learn is on how to utilize new experimental technique to answer our questions. For instance, we started thinking whether we should use X-ray computed microtomography to have a closer look how paper structure looks like on exactly the length scales that we need. And this is not super simple, but very, very worthwhile to do. But methodologically, we also have to learn a lot. This starts from simple consideration how to perform the experiments and also more advanced consideration how to do a proper statistical analysis of this enormous amounts of data that we come up with. So my biggest and most joyful news I can give on top of everything is that we have the situation that the very old, very clever, very simple and very instructive experiments that have been done on paper in the 1930s, 1940s, 1950s have been clever and instructive, and now we can see on the microscopic scale why the expectations that they formulated so long time ago do hold. So that's really something that is we can immediately go forward and now go more in the microscopic discussion, and we are confident that we hit something that is realized in real life. So it's a real life material, things can be tested, and of course everything we do can now be, of course, justified.
So it seems there's a constant interplay between these experimental techniques and also what you know from, let's say, how to phrase it, first principle in a sense from this microscopic description. So also like finding an explanation which holds at the microscopic level is not as easy as it would seem.
Yes, it's a fairly tight feedback loop because you have to deal with a lot of assumptions to make at least some of the problems truly tractable. And the only guide that we have very often is to inspect the experiment, whether we are on a good track or not. But this is the fun of it, to be honest.
Yeah.
A method that is widely used now in different areas is our neural networks, right? So
Yes.
are you using this in your research?
Yes, and in fact, to be honest, I was surprised in exactly which section it suddenly popped up. There are two things. The first is, I told you that we try to use X-ray tomography to look into our paper. And what you get out of that technique are beautiful three-dimensional images. But in order to really proceed further and to feed that information into a transport simulation, you really need to analyze these three-dimensional images in terms of what is fiber, what is a pore that is filled with air, is that a pore that is filled with a liquid, with water, for instance. We must be able to discriminate. And even though you can think naively, yeah, there is a contrast in the images that allows us to distinguish that, it's not always at every position in our 3D image as easy. So you have to be able to make a decision. What do I see? And it turns out that the pattern recognition power of neural networks is helping us there a lot. So we put a lot of effort in there, but we more or less abandon the previous effort and we go for methods that are powered by neural networks. Big data, a lot of data to learn. So these networks perform super nice.
Big, beautiful data.
Yeah, really big. Really, yeah.
Really big.
So the second thing is, and this was the even bigger surprise, is that clever people realized that neural networks can pose a very clever route to solve partial differential equations, possibly in the most natural way, provided that you have some extra data that you could squeeze in the problem. And finally, so when we were right in the middle of discussing how we are going to battle our partial differential equations, that are models that contain or rely on some information on the material that we do not necessarily have, right in that moment there was a sequence of publications where this method of physics-informed neural networks was really nicely propagated, really hands-on. And so we could start playing with that, and it was beautiful. So it's a method where you essentially use a neural network just to mimic the solution whose behavior is described by the partial differential equation.
So what's the difference with this physically informed neural network and a normal neural network? Because I can figure that out, but then which are the constraints you
so
take
in
into
essence, the core piece is a neural network, a neural network of your choice. So that's as one is used to from neural networks. But as you know, as you try to convey what the neural network should approximate, you give it the deviation from the desired prediction is entering a loss function. And rather than just comparing the quality of our prediction against just experimental data, what you can also ask is whether the solution that you predict is also having the right slope and the right curvature at a number of desired points. And the cool thing is you can ask wherever you want whether this condition is fulfilled. And the condition is very simply provided by just reading off the partial differential equation, because this is what the differential equation does, right? So you can really probe on all spots that you would love to, whether the predicted solution is in line with the physics. This is where a partial differential equation comes in. And then the differences that may still pertain are via increasing optimization cycles more and more minimized, such that in the end of the day you have a neural network that has been trained in a way that it really obeys the differential equation on one side and the experiments on the other side.
Would you say that in your field, the new discoveries are more theory-driven or more experimentally driven?
So right now we see a lot of momentum towards trying to optimize what we learn from experiments. And what we also see is that we have a lot of clever model ideas that are just sitting there and we're waiting that are fed now with that information, and it appears it takes off now big time. So we have now also other colleagues in different countries who come up with beautiful predictions on processes that are then using paper, by being able to really tell the paper under this condition is going to behave such and such, and therefore the result is going to be this and that. So that the pure theoretical modeling of transport is, progressing, possibly not as big velocity as other things, but the predictive power is increasing now very, very quickly.
Coming to modeling again, which are the big challenges you face in order to describe these materials? Like, if you have to start with a given material, then where do you start?
That really depends on, in my experience, I have to say that it depends really on the question that you would love to ask. So just to give you an example, we were asked, well, just can you try to understand better how gas molecules are going to interact with the fibers in the paper, and therefore having a certain impact on how well you can transport gases through. Yeah, and if you think about it, the first time you would also think, well, paper fibers contain is more or less a big hollow tube, and the tube walls are consisting of a number of layers that contain mostly semicellulose and lignin to some extent, and they are organized in a very elaborate fashion. So is there a way that we could imagine how the surface of such a fiber looks like, and how the chemical interaction with, for instance, water could look like, and can we predict, like in a capture and release way, like Monte Carlo wise, how the molecule makes its way to paper? Not such a good idea.
Try again.
just to get you a feeling for, to get the transport through a sheet of paper modeled, you have to cover at least 40 microns in thickness.
Okay.
You would not want to follow the transport on a sub-nanometer scale
For
such
40 microns.
that you could really make something useful out of it on the relevant scale. So this being said, I have to say we are most of the time more top-down. So we try to get the sheet perspective. And if I say sheet, it's mostly the thick perspective, properly described, or let's say satisfyingly described such that we can make prediction. But then, of course, curiosity driven, we would like to get deeper and resolve details more. And right now we are on the level of trying to elucidate better, for instance, the fiber walls are going to interact with the molecules. They change the structure, they change shape, which makes everything more difficult, even though more interesting. But we are far off really resolving cellulose molecules.
What is your sort of dream long-term goal? Like, what would you be very excited about if you discovered in like 10 or 20 years, sort of? Or where there's maybe an application for it that you drove with your discoveries or something like that?
Or maybe, is it already the case? I mean, did you?
So on the small scale, something like that indeed happen. So the small scale means something that is gratifying for each scientist if you lay out a project and you are asked to be ambitious. So you try to come up with a vision that is really worthwhile to pursue. And after 7 years, you figure out, oh, well, look, come on, we did it. That's, of course, awesome. Mm-hmm. And I have to say that's something that is not going to be immediately materialized in application, but is, however, used by our partners to design applications in the future. So that's, of course, great. To be honest, what I love to say is I was dealing a lot with materials in my past. So I'm after structure to property relations. And I find it very much gratifying if a structure to property relationship emerges. This can be very often things like, in my past, I have a semiconductor of such and such properties. I put it in a device with another material and all of a sudden something doesn't work. Just to really give a clear answer why things do work and why they don't work. It's really a piece of the puzzle just put in the right spots to keep people afloat. So it doesn't need to be the big thing. Mm-hmm. What very rewarding is to keep the ball rolling, to find things that are interesting, to find things that you can tackle, you can contribute.
What do you expect in coming years? Like big results coming from experiments, or as you said before, like very small steps, one after the other, then will provide a new understanding or new challenges possibly, and then...
that's a very intriguing question. Yeah. It can just be an opinionated answer, of course, which is, of course, driven by what I see. So right now we are in the era of big data and artificial intelligence. And as you know, that involves right now still collecting a lot of data. So it's not so obvious for me to say what you can do with all this data that you collect. But I see that we have here and there a number of game changers that are really fun to play with. So we see that on the all-day level, for instance, that the support that we have with languages and language models, that help, absolutely. Then in terms of, how to say, really having the data that empirically help to understand things, this is also something that has been gaining speed a lot in the past years and shows effect. Yeah. So, however, the big thing in my field that we design an experiment that would not be possible without the methodology that we have, I would not dare to make a prediction, but I think there are candidates there that do exactly that thing. So we have very, very, how to say, elaborate experimental setups that would not work if we would not just permanently just process the raw data and put raw data from different points of measurements immediately into a relation just to come up with more information. You know the old problem that you cannot measure amplitude and phase of a wave function at the same time. So guessing the phase and recording the amplitude at the same time, so there are amazing progress achieved these days. So I think in that direction there will be a lot coming soon. Also in spectroscopy to clear up the signal, to be sure what is noise, what is a true signal from the sample. So I would say these are the things I would expect give us more and more insight, better resolution, and better control.
So there is room for improvement for sure.
There's room for improvement.
Okay. And there is the need for students to do so.
Oh, absolutely.
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 Okay.
There's absolutely no way to do things without the clever and engaged students that we have.
So you would strongly encourage everyone to contact you.
Yeah, but anyway, of course. Well, yeah. Of course, I would need to promise also to write associate proposals. But let's say more in hindview, I have to say, it's the enormous progress that we enjoy is just plainly due to the effort and the cleverness and also the communication between the students. It's awesome. Yeah.
Did we forget something you'd like to talk about more in detail?
At least I can try to give you a flavor how we are operating. It's sometimes enormously funny, I have to say. So we are very, very happy about the opportunity to be able to probe the microstructure. We can do this in-house and we can do this with X-ray. And I tell you, this is so important because paper can't stand electrons. We have super nice electron microscopes across the strait, but they unfortunately burn our paper away in the course of the investigation. So I'm afraid if the colleagues over there hear the keyword cellulose, they just block the ears and say, ah. So they don't like to handle that material a lot. Well, it's really challenging. It's much easier to get information with X-rays. And we can think about experiments that allow us, for instance, to monitor in situ how the structure of a certain material reacts to a certain external trigger. For instance, in paper, very obviously the interaction with water. We notice ourselves if we just pour our water on our napkin, something happens. And this has an immense impact on the internal structure, and that's something we would love to follow. But in order to do so, we have to come up with contraptions that allow us to create exactly these conditions in the machine in the basement. So, and that's the reason why we have indeed also experimental efforts in our group come up with designs of experimental contraptions that can be inserted in the stage and that allow us these kind of investigations. And this is really on the level of, how to say, bring simple things together in a clever fashion. So we have pickle jars put in an aquarium pool that are coupled with aquarium pumps, things like that. And these contraptions do a grand job and help us a lot in insight and can also be ported somewhere else. So we have a little chamber that looks like a fish tank, and you can put somewhere and put your paper and you could put something else in, and you can see on the fly what's going to happen. So that is a big branch from really most sophisticated kind of investigations with tomography to something that is really simple, made with, how to say, all-day homemade tools put together. So that's fun. Yeah.
Okay. Thanks for this insight.
Yeah, even though your simulations, if you have to do things hands-on, don't worry. If you have two left hands, just try.
That's the spirit.
Yeah. You are first principles persons, are you?
Yes.
Yeah. So possibly, if you like, I can comment a little bit on the first principles.
Yes.
So I have to say, it's not the tool of choice as far as my topics are concerned, but definitely they are not completely out of discussions, of course, in no way. So the thing is that we have fairly heterogeneous complex structures to deal with. And as you possibly know, with atomistic simulations, it's not so easy to mimic such a situation because you plainly need a lot of atoms to do so. Nevertheless, there have been a lot of very appreciable progresses made also in molecular dynamics. So really reliably predicting how atoms would like to move in an environment that's also adequate for fibers. So we do not have any planar arrangement, but it's on a big scale somewhat roundish, but all over the place. So something like that can be in part already generated and also reliably probed, for instance, in terms of seeing what water molecules would like to do, if they would like to wiggle into crystals that are formed by cellulose strands, or whether they would rather wiggle into fibrils that are formed by cellulose chains. So that things start to work nicely and start to be corroborated also by experiments. So things come.
But they are limited to some, like, for example, I don't know, thickness or just some size, because you said
They are
before,
limited by size, of course. Yeah.
So do you think these methods, as they evolve and as also computational power increases, at some point would be capable of simulating transport through paper fully on a molecular dynamics basis?
This I don't know. This is a lot to ask for. And so there's some important step that has to be established in between. And this is related to the variation that our molecule is going to experience as it goes along the paper. So there's a lot of variation. So many different situations can be realized. Suppose you have a grasp on how this variation looks like, then the chances are good. Because then you don't need to have the full path. As long as you know that such and such variations are such and such likely encountered, there you are. So that you can have a smaller scale simulation made, and then from looking at how different realizations of such simulations look like, you can come up with an entire prediction. I think in that direction, chances are very good.
So in a sense, extrapolating from something small, but then if you expect this to be, replicated in a sense,
Exactly.
like on a larger scale, you can infer something. Okay.
Like imagine you take this piece of paper and you fold it multiple times, then it's a very big sheet. Then if you send something through, it's going to realize, or it's going to see many different environments as it goes through. Many more as if you would just send it straight to the sheet of paper as it would be here. And this could be the trick, that just statistically thinking about, do I have seen? Which fraction of situations I have seen? And which fraction of situations I must have seen in order to be predictive. If you have this under control, there you are.
How much do you enjoy being a researcher? Because you seem very enthusiastic when you talk about your research.
I'm enjoying in particular the research part. As a professor, you have also
Duties.
other duties, which is in order to run research, you also have to do some administrative stuff. Sure. And I really savor, the discussions with the group, and also the few hours that I can sit myself in front of the computer and write my own code and try things myself, just in order not to lose some of the skills that you have developed as a younger person to try out yourself what you have in mind. This is really, as you know, truly rewarding if things work out. Yeah. This being said, of course, also teaching is important, and teaching is broadening the perspective so much, and getting an idea of what is needed to convey things, and from your own experience, what would be nice to have to demonstrate things. These things utilize each other very nicely. Yeah. So it's still effort, and still, how to say, it's not the research I would love to do possibly today, but still you get the increasing feeling that things just get together and are helpful in many different directions.
Thank you very much for this chat, Karin. It's been a pleasure.
You're very welcome. I enjoyed it as well. And
see you next time.
See you next time, and maybe we have some point of view provided by you guys.
So, thanks for listening.
And hear you next time.